Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, this is perfect. We're getting like a 7-minute rule here. Okay, we're exactly 6 minutes after, so looks like most people should be here by now. It's my pleasure to introduce Ana Maria Popescu from the University of Washington. She got her bachelor's degree from Brown and her master's from the UW, and she's currently working with Orientation on KnowItAll and on this system called OPINE, which is about mining product features and customer opinions. And that's what she's going to talk about today. And if anybody wants to meet with Anna, I think there's possibly still some more time in the afternoon where we could schedule something. So if that's the case, just let me know. Okay.
Thank you. Hi, I'm Anna, as you just heard, and I'm going to talk about our work on mining product features and corresponding consumer opinions from customer reviews. So this is work done under the supervision of my advisor, Professor Ornetioni, and made possible by the KnowItAll research group at the University of Washington. I'm going to start by talking about some related work in the area of mining customer reviews, and then focus on our system, which is named OPINE. OPINE addresses a number of tasks, but I'm going to focus on two of them, the product feature extraction task and the customer opinion extraction task. Finally, I'm going to draw some conclusions and talk about what we're currently doing and what we're planning to do in the future. As some of you know very well because you're working in this area, there's been a lot of work in natural language processing on identifying subjective phrases or sentences. So this means distinguishing between subjective and objective text, as well as on analyzing this kind of subjective text. So figuring out whether it is positive or negative. So this is called polarity classification. And also figuring out how strong the sentiment expressed by a particular phrase or sentence is. This natural language processing research has been used by a number of the same people and many others to classify consumer reviews, classify them as a whole as positive or negative, and also determine, again, how strong the sentiment expressed by a particular review is. So is the review weak, strong, very strong? In the past couple of years, people have moved beyond just labeling whole reviews and actually mining the review text for more detailed information about a particular product. So such information might include names of the product features which are mentioned in the review and customer opinions corresponding to each feature. The customer opinions can be either opinion phrases or opinion sentences. OPINE is the system that we've developed. It's a review mining system that follows in this line of work. So here's an example of the kind of output that OPINE currently produces for the hotel domain. In this case, we're looking at the Mandarin Oriental New York hotel, and the system starts with a set of reviews for this hotel and produces a summary of these reviews. What I mean by a summary is, first, the system identifies the names of features, hotel features, which are mentioned in such reviews, things like service, staff, room, food, etc., and then finds opinion phrases for each particular feature. So if you look at the service feature, you'll notice that opinion phrases include things like discreet, attentive, excellent, good, and so on. Some of them refer to the quality, to more specific qualities of the particular feature. So for example, discreet refers to service discretion, whereas things like attentive refer to service attention. So one thing that we try to do is actually cluster these opinion phrases to get even more specific information about what particular qualities of the features are implied by the customer. In addition to fabricating these feature names, the system determines whether a particular opinion phrase is positive or negative, so the polarity classification task. And then it also determines whether a particular phrase is stronger or weaker than another phrase. So for example, in the case of the room beauty feature, which is in the highlighted box, the absolutely beautiful opinion phrase expresses a stronger level of sentiment than just beautiful. And in this case, the opinion phrases have the same main word, which is beautiful, but the system does this for any two opinion phrases regardless of the lexical overlap. So you will find, for instance, that fantastic is just a stronger opinion than great. The polarity classification and this kind of relative opinion strength can be used by the system, is used by the system, to compare two hotels based on how people feel about a particular feature. So what the system is doing right now is using a very simple aggregation function to just aggregate the consumer opinions about, for instance, the room beauty feature and compare two different hotels. So in this case, 33 other hotels, including the Premier Hotel, are reviewed by customers as having rooms which are less beautiful than this particular hotel. So we haven't exactly looked at what the best way to summarize consumer opinions about a particular feature is. We just use some very simple average to compute this. But this is just to show you that if you have something like this, you can navigate in the space of products, in this case, in the space of hotels, for a particular feature. I'm sorry, you mean things like the hotels and things like that?
No, it's like service, room quality, or service or beauty, things like that.
Oh, so these are extracted from text.
Okay, so the categories themselves also.
The categories themselves are extracted from text.
Cool.
So, like I said, the first thing that is extracted is the word room, and then based on what opinion phrases are found with room, those are classified as, some of them refer to the room beauty, and some of them might refer to how clean the room is, so the room cleanliness and so on.
So then if you're looking at two different hotels, you
Yeah.
might actually have different categories
Yes.
then for them. Oh, I
Yes.
see.
So, you'll notice that some of the, so we were sort of trying to get as detailed as possible. So some of this might be too detailed. You might not want to have these very fine-grained attributes. You might just want to have, the room has these opinion phrases corresponding to it, and then you can use those to compare two hotels, because some of these don't appear for more than 2 or 3 hotels.
You're saying that you're comparing
Yeah.
to, then you cluster over both of them for the categories?
Yeah, that's right. So it's compared with respect to this final feature, like room beauty, right? Yeah. But again, you don't need all of these. You can just aggregate some of them and
So is the system intelligent enough to detect that if the same reviewer
Yeah.
say absolutely beautiful for all the review that he gave for all the hotels,
No.
it's likely to calibrate it down?
No. So right now, the system makes a number of assumptions. One of them is that it's not going to deal with that case. So it actually doesn't account for the profile of the user. It doesn't look at this particular user. Does this user maybe favor hotels in New York? Some people review positively everything. They like everything. Some people don't like anything. But the system doesn't look at that. So it doesn't account for the user, what the user is like. But that's something, if you actually were to use this to produce, say, a realistic comparison of hotels rather than just show what you can extract from customer review data, then you'd want to take into consideration the user information as well and condition on that. Yeah. Yeah, people always ask, how close is that to, does that actually give you a ranking of hotels? And what you find is that the good hotels tend to be reviewed better. But I don't know if each particular hotel is actually reviewed accurately. Yeah. So I'm sorry.
How large was the set of data that you were working on?
So for this particular domain, for the hotel domain, we have something like 10,000 reviews, or I think even more. We've done our experiments on a smaller set, but then we just sort of applied. The demo that I have is on 10 or 15,000 reviews. Yeah. So the 2 tasks that I'm going to focus on today are, first, identifying product features which are mentioned in a particular review. And this is something the system does pretty well. So the precision is 94% and the recall is 77%. And then the second task is identifying the semantic orientation of a potential opinion word in the context of a given product feature and a review sentence. So the potential opinion words can be adjectives, nouns, verbs, or adverbs. And what I mean by identifying the semantic orientation is simply detecting whether the potential opinion word is positive, negative, or neutral. So if it's neutral, it is in fact not an opinion word and it's discarded. And this information can then be used to identify opinion phrases. So as you saw in the previous slide, sometimes people say, this hotel is absolutely beautiful. So absolutely beautiful is an opinion phrase rather than just a word. And then identifying the polarity of the opinion phrase as well. Just one more thing before I go into what OPINE actually does. This is my word to our sponsors. OPINE is a review mining system which leverages an already existent information extraction system, which we developed at University of Washington. Some of you might have heard of it, so I apologize. It's called KnowItAll, and it's a web-based information extraction system that simply finds facts and relationships for a domain of interest by mining web text. And the main thing about KnowItAll is it has a couple of key ideas. The first one is its generate and test architecture, which simply means that the system first generates candidate extractions by instantiating these extraction rules, which are based on lexical patterns, and then uses high precision lexical patterns to weed out the incorrect extractions. So to distinguish between actual facts and relationships and just noise, incorrect facts and relationships. OPINE is built on top of KnowItAll in literally and figuratively, so it uses and it extends the KnowItAll architecture. And it also takes these two key ideas. The first one is that you can use high precision lexical patterns, such as the ones introduced by Marti Hearst in '92, to do a number of various things, such as extract information and then validate information. And then the second idea is that it pays to go to the web to collect statistics rather than focusing on a more restricted domain-specific text. So finally, let's see how OPINE finally extracts product features. The system starts with a given product class. So throughout this talk, I'm just going to talk about the hotel product class and a set of instances, for example, the Trump International Tower Hotel in New York. And for each instance, the system has a set of customer reviews, which express how various users felt about the particular hotel. So now, given this review set, the system goes and finds a number of different features. It can recognize properties, things like quality and size, physical parts, such as room, features of parts, such as room size. Then there are these other concepts which are neither properties nor parts, but are relevant to how the consumer feels about the hotels. For example, the hotel neighborhood is something that is deemed important. The city in which the hotel is located is something that people tend to express opinions about. And even more specifically, features of these related concepts, like the neighborhood safety. So the system has a very simple feature extraction mechanism. It first parses the review data, and then extracts the noun phrases. So it makes certain assumptions as to what constitutes a product feature. It extracts the noun phrases, which contain only nouns. So you can have the noun phrase length can be greater than 1. In this example, on the left-hand side, you can see the noun phrases which are extracted as potential features in blue. And finally, it extracts only those that appear more than once in the review set. Once the potential features are identified, the system uses a number of lexical patterns to distinguish between those corresponding to actual features of the product class and those that are not actually features. So these lexical patterns, for example, if you're looking for parts or properties of a product class, parts and properties are examples of meronyms. So the system starts with simple, highly indicative patterns such as X of Y, Y has X, or Y is X, which are known to be indicative of X being a meronym of Y. And then so these patterns are domain independent and tend to apply in a large number of cases. But the system can use them to bootstrap more domain-specific patterns. So if you look at some of the other ones, X equipped with Y or X boasts Y, these are things that tend to occur in reviews that you might not see these patterns in just open domain text. So once the system identifies a set of lexical patterns for each relationship of interest, it uses them to assess potential features. And it does so by computing a very simple measure, the pointwise mutual information measure, between the name of the potential feature, so for example, room, and then each of the lexical patterns which is instantiated with the name of the product. So in this case, hotels Y. So it simply looks for how many times hotels room, the combined phrase, occurs on the web, versus how many times hotels by itself occurs and room occurs by itself. So this measure is a measure that's inspired by Peter Turney's work. And in fact, a lot of things that we didn't know at all at the very beginning used simple measure and took advantage of the data on the web to do validation of extractions. So this is simply applying this to the task of finding product features. So you can see by the numbers for room and snow that the value of the measure tends to be much higher for words and phrases that correspond to actual features. And the system uses this discrepancy to basically builds a classifier that simply distinguishes between features of the product class and words and phrases which are not features. So after the classifier is run, things like time and snow, which are not in fact features of hotels, are discarded. So like I said, this is a very simple mechanism. Let's see how it does at finding product features. So we looked at two evaluation settings. In the first one, we compared OPINE with this system developed at the University of Chicago in 2004. Now, when we wrote this paper, which was like 6 months ago, this was the best system that we knew of. In the meantime, we found that there are other systems, some of which are developed here at MSR. They don't do this exact thing, but they do something similar. But more importantly, there's another system developed at IBM, which did something very similar to OPINE, and their precision is much higher than that of the baseline system found here. Their precision is 90%. But at the time, we only had, but we don't have their code or their data. The project is dead right now, so we can't compare it against that one. But I just have to acknowledge it because IBM put a lot of work apparently in their sentiment analyzer. Anyway, the baseline system that we, yeah, sorry. I actually have the reference. The first name is, I think, I'm going to butcher it. It's Junggi E. And then Wayne Nieblak, I think, was the leader of the text analytics group. They're all gone or retired. So I don't have their data order. But they've done some interesting work and they got good results. Their precision at finding product features was 91%. And then on the task of finding consumer opinions, they also got high precision, although much lower recall than we do. So the system that we knew of did pretty well. They have a much simpler approach. It's done by Hu and Liu, so it's a collaboration. And their approach for finding product features simply looks for frequent noun phrases in the set of consumer reviews. And it's a very simple approach. It just assumes that if something is mentioned a lot of times, then it's likely to be a product feature. And you can see that the precision is 72%, which is 22% less than ours, but still it's pretty high for such a simple approach that doesn't use any external data for validation. And the recall, of course, is a little higher than ours, is 80%.
Just by identifying a product class, it's a classification of any product that exists within that.
That's right. That's right. Yeah. Now, in order to see where the precision increase comes from, we do two things that the baseline system doesn't do. We first actually assess each potential feature to make sure that it's a feature of the class and not just rely on the frequency. And the second thing that we do is we use the web to do the assessment. So in order to see where the precision increase comes from, we've run this simple experiment where we run OPINE but deny access to the web. So we just use the set of reviews at hand to compute the statistics necessary for validating product features. And you can see that the precision of that system drops significantly. So what we found was feature assessment increased our precision, but what really boosted our precision was the fact that we used the web to get product validation. And of course, this makes sense because the web is the ultimate source for product reviews. So you're going to find a lot of information about what's a product feature and what's not. So the first evaluation was done on the consumer electronics product classes, which are used in the Hu and Liu paper. And then we did an additional evaluation on two additional product classes, the hotels and scanners ones. And we obtained, this was just done to make sure that our system can address other domains very well. So we looked at hotels, which is totally different from consumer electronics. In fact, we found that hotels is much easier than consumer electronics. And we found an 89% average precision and about 73% recall. So now, one thing that we noticed is that with the approach that we had taken so far, every time we were going to a new set of reviews for a product, we weren't exactly sure that we had, we were going to have to run this product feature extraction on top of that set of customer reviews. But it makes sense that you would want to run, you'd want to have a set of product features for a particular product, and not necessarily have to, and just use it for an incoming set of reviews in order to find these features in the text, and not have to redo the validation for each set of consumer reviews. So what we're looking at right now is building a more complete set of features for each particular product, which you can do by starting with a set of reviews and then just using the web to augment the set of features, not just for validation, but also to get more names. And you can do this because features tend to occur on the web in these enumeration patterns, X, Y, and Z. So people actually tend to tell you what the features of the product are if you just bother to search for these sentences on the web. So this is something that we're trying to do right now, so we can build this more complete set of features. And then every time a new set of consumer reviews comes our way, we can just use those features to do extraction of product information. So we looked at how we did product feature extraction, and now we're going to talk about how we do the extraction of corresponding customer opinions about each particular feature. So first, given the set of reviews, we identified the names of the known features in text. So you can see them on the left-hand side in blue. And then we use this intuition, which is similar to intuition used by other people before us, which is that if you're looking for an opinion phrase corresponding to a feature or a concept, that opinion phrase is likely to occur in the vicinity of the concept in the sentence. So this makes sense. So other people, like Hovey in 2004, used windows of variable size to find such potential opinions. And then the baseline system I referred to before, Huan-Liu, uses just as a part of speech tagging of the sentence and uses something similar, so just a window. So what we do is we just parse the sentence, and we have these syntax-based rules which search for potential opinion words which are in the vicinity of the product feature name. So for example, there are two examples of such rules. The first one says that if a sentence contains the name of a known product feature as a subject, and then the corresponding predicate contains the verb to be or some synonym of to be, then the predicate argument is extracted as a potential product feature, as a potential opinion word. So for example, if you apply this rule to the second sentence on the left, the system extracts broken as a potential opinion word corresponding to the feature fan, and hot is a potential opinion word that corresponds to the feature room. Once the system extracts a set of corresponding opinion words for each identified feature in the text, it then seeks to classify them as positive, negative, or neutral. And it does so taking into consideration the feature to which they refer and the sentence in which they occur. And the reason for including the feature and the sentence information in this computation is that we found that, for example, in the hotel domain, there are many words that change their semantic orientation based on context. So here are some examples: hot, visible, casual, modern, central, and so on. Some of them are actually the ones that are mentioned here have this problem where sometimes they're neutral. So sometimes someone just happens to notice that the hotel is central, but doesn't actually express an opinion about it. It's just a descriptive statement. But sometimes the fact that the hotel is central means that there's a lot of noise and a lot of other problems, and therefore the opinion word is actually negative. It's an opinion word, first of all, and second of all, it's actually negative. So words like this, in order to figure out the correct semantic orientation, you also have to take into consideration the context in which they occur. And we're trying to model context by saying, if you're looking at the feature to which they refer, and if you're looking at some context in the sentence, you can do better at finding their semantic orientation. So the solution to this problem has 3 steps. We first compute a dominant semantic orientation label for each word. And the reason for this is that although some words change their semantic orientation, there are still enough words which are reliably positive or negative, regardless of whether they occur. Things like nice, awful, and so on. So reviews are rife with those. So just finding the dominant semantic orientation label for a word will pay off. Then we find the semantic orientation label for each word in the context of the corresponding feature. And finally, we include the sentence information and find a semantic orientation label for each word in the context of the given feature and in the context of the sentence in which it occurs. So each one of these steps is a labeling, corresponds to a labeling problem. So we use the same underlying mechanism, which is just a relaxation labeling mechanism, to solve them. For those of you that might not be familiar with relaxation labeling, it's an unsupervised technique that we borrowed from computer vision, and it's similar to a number of other energy minimization techniques that people have looked at in the past year or so, we've noticed, for opinion mining. What the technique does is simply takes a set of objects and a set of labels which have to be assigned to the objects. It assumes an initial assignment, an initial labeling, and then it takes into consideration constraints on the labels of each object, which are placed by the other objects in its neighborhood. So it assumes that the object's label is influenced by the labels of other objects. The way in which the neighborhood of an object influences its label is modeled by the support function. So this is an iterative algorithm that starts with the initial labeling and then at each iteration updates the probability of each label for each object based on the value of the probability computed at the previous iteration and the current configuration of the neighborhood of the object. So it simply computes a global labeling which best satisfies, for some definition of best satisfies the set of constraints. The algorithm finishes when the method stops basically when the set of labels doesn't change much between iterations, or it doesn't change at all. Or if you want to be even more, if you want to wait longer, you can wait until the probabilities themselves don't change their value. So here's how OPINE computes the dominant semantic orientation for a word in the context of relaxation labeling. So in this example, I'm going to focus on the word hot, which, as we've seen before, has this interesting behavior that it can change its semantic orientation. In the first sentence, the word loved is found to be connected to hot by means of the syntactic dependency path. If you actually look at, so we're parsing the sentence and we're using this dependency parser. And because love is connected to hot by means of this dependency path, love is extracted as a neighbor for the word hot. Another neighbor is clean, which is found to be connected to hot by means of another path, which is actually dominated by the conjunction and. These two neighbors, because of how they were extracted, because of the extraction patterns, are found by OPINE to have similar semantic orientation labels to that of the target word. So the system thinks that love and clean have the same semantic orientation label with hot. In the second sentence, we found another neighboring word, which is spacious. However, in this case, spacious is connected to hot using the disjunction but. So the system thinks that spacious has a semantic orientation label that's different than that of hot.
I guess I don't really understand. So you have parsed this sentence.
Yeah.
What parser did you use?
We used the minipar dependency parser. Yeah.
So how is it that you formulated the second of these kind of hypotheses that there's a neighbor, hot, clean, and? How did you derive that from the parse tree?
Yeah, so that's derived. So what we do there is we take into account, it's a little more involved. So we take into account not just the word information, but also the feature to which the word refers.
Right.
So it looks for the fact, so it finds that, in fact, hot modifies water, which is a known product feature. And then water is conjoined with bathroom. And therefore, it extracts clean. So it basically assumes that it basically finds two word feature pairs, which are conjoined by a conjunction.
And that is constrained by the
And that is, yes, that's right. So it also takes into account the fact that you know the feature name. And this is a heuristic, right? It just says if two word feature pairs occur and they're joined by and, then the words are likely to have, the opinion words are likely to have the same semantic orientation.
So how many such patterns, syntactic patterns, have you encoded?
So this
because
is
you have to have specific ones for each of the discourse connectives.
Yeah, so we have, I just counted them as the level of heuristics, but then each heuristic has to be explicitly written out for the system to use. So there are about 10, 15 heuristics, but there's a lot more actual patterns that can be automatically, so there's kind of automatically derived, but you have to actually write down the heuristics.
Right.
Yeah.
Actually, is it even true that when you have a conjunction that they're in the same direction? I could imagine that there's also, you can conjoin things on a scale like hot and cold, or tall and short.
So what we did here is we looked at, these heuristics are not new. So there are people who've done work in this area and sort of looked at whether conjunctions actually link words with the same semantic orientation and so on. And they found that that's mostly true, although not always true, because you can imagine even two words that have different semantic orientations and are linked by and. So that actually happens. But we looked at the fact that people had used this and found them to be quite precise, and we simply generalized them to maybe allow for not just words to be conjoined, but also word feature pairs. So this
saying the arguments of them are also.
I'm sorry.
Well, the arguments of these things are also going to share something. Right?
Yeah. So this is. There's a lot of work that's been done on measuring whether these heuristics actually work. People found that they work, although there are cases in which they conjoin arguments with different semantic orientations. Yeah. So in addition to, so these are syntactic features, But in addition to syntactic features, we've also looked at including synonyms and antonyms from WordNet. So what I mean by that is the word clean occurs in the first sentence, but if you find the word neat in some other sentence in the corpus, neat and clean are synonymous in WordNet. So we say that clean has the same semantic orientation with neat because they're synonymous. And finally, we've looked at ISA relationships. What I mean by that is, I can't remember the exact example, but for example, for nouns, this happens a lot. So you can have, a problem is an example of hazard, or I think the other way around. A hazard is an example of a problem. So if you find two words that are linked by ISA in WordNet, and they are likely to have the same semantic orientation. And finally, the morphology information. The morphology information is useful, especially for adverbs. So you can imagine the reviews are full of adverbs like wonderfully and awfully and so on. And those tend to have the same semantic orientation with the adjective that can be obtained by just removing the suffix. So here's what the system actually does. It first initializes the probability for each of the potential labels, positive, negative, or neutral, for the word of interest, which in this case is hot. And it does so by using a modified version of Peter Turney's PMI-based method. This method, for those of you that might not know, simply looks at whether a word predominantly occurs on the web in the vicinity of positive or negative seed words. If it occurs with positive words, it's more likely to be positive. If it occurs with negative words, it's more likely to be negative. And what we sort of modified was that we said that if it occurs with neither positive or negative words, it is more likely to be neutral. That's not, again, not always true, but it's just an assumption that we made so we can get an initialization. You can imagine other ways to initialize these words. We didn't look at this, but there are lexicons, like the Journal Inquirer lexicon. So you can start with a much better list of positive and negative words. Once the words are initialized, the system builds the neighborhood for each target word, like we've seen before. And then in the relaxation labeling update step, it takes into account the constraints that are placed on the label of each word by its neighbors. In this case, hot was found to be initially mostly positive in the hotel domain. So this is per domain. And then after the data was taken into consideration from the consumer reviews, the system increased the support for the positive label for this word. However, computing the dominant semantic orientation is not enough because, as I've said before, many words change their orientation based on, for example, what feature they occur with. So typically, when hot occurs with features such as water, it has a positive semantic orientation, but when it occurs with features such as room, it almost always has a negative semantic orientation. So in order to take into account this behavior, the system then computes a semantic orientation label for each word in the context of the corresponding feature. So here's an example. When the system tries to figure out whether hot room is a positive, negative, or neutral word feature pair, it starts by assuming that it has the same configuration with the potential opinion word itself, which is just hot. But this is clearly incorrect because it assumes that hot room is more likely to be positive in the hotel domain. However, if you compute the neighborhoods for this particular word feature pair in a manner very similar to what I've described before for just words, you find strongly negative word feature pairs, such as stuffy room, broken fan, and so on. Also, you find modifiers, strongly negative modifiers, such as unbearably, which are extracted from formulations like, this room is unbearably hot. Therefore, for this particular word feature pair, when you take into consideration the kind of other the kind of word phrases it occurs with in the corpus, in the relaxation labeling update step, the label is changed from positive to negative. So hot room is found correctly to be mostly negative in this particular corpus. However, regardless of whether most people dislike a room being hot, there are contexts in which a hot room is actually desirable. So this is an example. This doesn't happen very often, but it does happen sometimes. So in this sentence, I like a nice hot room when the snow piles up outside. The system starts by assuming that hot room is negative because that's the dominant semantic orientation for this word feature pair, and then takes into account the fact that it occurs with strongly positive word feature pairs, such as nice room or like room. And therefore, in this particular sentence, the orientation of the word feature pair is changed, again, from negative to positive. So let's see how well this algorithm does. We've compared it with two baseline systems and a version of OPINE. The two baseline systems are a version of PMI, of Peter Turney's PMI-based method for finding the semantic orientation labels of not just words, but also phrases. And we've used this method because it allows us to not just find the semantic orientation for the word clean, but also for the phrase clean room. So it allows us to include the feature information in the method. And this is basically an example of contextual information, which the method accommodates. It, of course, doesn't accommodate the sentence context because you can't figure, it just uses the web to figure out the semantic orientation of a phrase. So it doesn't know for a specific sentence in the consumer review that we have whether that's the correct semantic orientation or not. The second method that we looked at was a very simple, very simple WordNet-based method for finding semantic orientation labels. This is a method that was used by the system of WhoLU, which I've introduced before. They don't take into account any contextual information. They simply start with a set of positive and a set of negative words, and they used synonyms and antonyms from WordNet to augment the sets. And then for each incoming word, they determine the semantic orientation of the word based on this augmented set of positive and negative words. So their method works pretty well because they start with a large set of positive words, large set of negative words, and then if you, once you put in the synonym and antonym information, the two sets become quite large. So it does account for a large number of the words which are present in consumer reviews, mostly because these are pretty common words. Finally, we looked at a version of our system which doesn't take into account feature information or sentence information and just computes the dominant semantic orientation of each word. So what we see is that the baseline systems actually do pretty well, considering the fact that they don't take into account, one of them doesn't take into account any contextual information, and the PMI method only takes into account feature information. However, we do see that OPINE on the whole has better precision, although its recall goes down a little bit compared to PMI. So what we've seen is that the improvements of OPINE are mostly due to the fact that we include feature and sentence information whenever possible. And this means that we find the correct semantic orientation for a word in context in more cases. Finally, we've used this algorithm for finding the semantic orientation of words to identify opinion phrases. And we've done, so the numbers here mean that when the system was evaluated on the task of distinguishing between phrases which correspond to opinions versus phrases which do not, the precision is 79% and the recall is 76%. What I mean by 76% is it actually finds 76% of the opinion phrases. Now, some of you know that an opinion might be expressed by not just a phrase, but a longer segment of the sentence. And we do not take this into consideration here. Because if you take that into consideration, the recall actually drops further, and it's around 60%. So there are a lot more types of opinions that we don't identify. And finally, once the opinion phrases are identified, we look at whether we can classify them correctly as positive or negative. And we can do that pretty well. So what are the issues with OPINE? Well, it has many issues. It doesn't know how to deal with parsing errors. So since we use a parser, we have a lot of parsing errors. Parsing errors can lead to actual opinions to be missed. So for a particular feature, there might be an opinion phrase expressed in text. But if it is not expressed in the vicinity of the product feature, then the system sometimes misses it because of parsing errors. Also, the system might miss negation words or phrases, which should be taken into consideration when determining the final polarity. Also, it might not recognize them, so they might be expressions that the system just doesn't know. There's also sparse data problems, which any system suffers from. For infrequent opinion words, the system doesn't have as much data to use to figure out the polarity assignment. Finally, as I've said before, a lot of data, especially in the consumer electronics domains, have complicated opinion expressions. So these include things like nested opinions, or conditional expressions, or the presence of the subjunctive, and so on. So what the system does is try to figure out when it finds itself in one of these situations, and then it refuses to label the opinions because it doesn't have a module to deal with these complicated expressions, and it would just incorrectly label them. Yeah.
big source of problems, much more in
Yeah.
consumer electronics versus hotels, is that people would talk about other products in the context of the reviews. They'd say, like, whereas the Sony MDP is blah, 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 this one is something or other. I mean, does that...
You mean because they mentioned the names of other products?
Yeah, and then they'll start describing those.
Yeah, so what I found was, so what I looked at, so I was actually looking at it on a sentence level, right? So there's a set of numbers, which I haven't presented here because I haven't finished those experiments. But you can look at other things as, for example, you can look at, do you actually identify features that correspond to the product of interest? So if the product of interest is some version, some particular laptop, and not the next version, right? But the review mentions both of them. Figuring out whether the feature that you identified is not just the feature of a laptop, but the feature of the laptop that's reviewed in this particular review. So I don't actually have those numbers, but we try, if on a sentence level, we try to figure out if the name of another product is mentioned, and we don't take into account the features that refer to it. However, you can imagine that at the level of the review, they can introduce it over here and then just mention it for 10 sentences without referring to it. If it's a next version of the same exact product, you might not even figure out. You just think, oh, it's the same laptop. So we make certain assumptions. One of them is that one review predominantly reviews one particular product. Again, that's not exactly true. If they mention other products at the level of the sentence, we can find that. If they mention other products and then keep referring to it, we can figure that out right now. Yeah.
Product class or product do you guys use to look through the opinion? Like, for example, for hotels?
I mean, we've detected, let's see if I can remember. So for hotels, we have, in terms of the number of features that we use for hotels, we use something like, I think it's 400 different attribute names. Yeah, so far. Now, again, what we found is that some of them should really be clustered. So one thing that we haven't done is, if you look at the actual names, some of them are somewhat synonymous and could be clustered together. So yeah.
And how is that in relation to the precision numbers you get for opinion extraction?
The opinion extraction simply looks at if you recognize the feature in the sentence, can you find the opinion that's associated with it?
Well, I guess my specific example would be, let's say, a digital camera, and if you have detailed attributable information about that digital camera, megapixels, speed attributes and stuff, and those are actually pretty precise.
Right.
How much do you think that's proportional to your precision numbers that you were talking about versus a shallower set?
You mean the ones right here?
Yeah.
So the ones right here assume that you've identified, so it doesn't include the feature information at all. It just looks at one sentence. The feature is kind of assumed to be labeled, although we just use the ones that we've identified automatically. And then for the ones that we've actually found, it looks at, can you just find the opinion that's associated with it? It doesn't look at whether you can find both the features. So the numbers are not cumulative. They're just for opinions.
Oh yeah, I understand. I'm just wondering how in this precision number does it help to have those exact key attributes?
Oh, you mean how well would we do if we didn't use the feature information?
Or proportionally, if you increase that, what's the relation?
So I think the number that would change is if you look at the different number, which is how many of the opinion phrases do we actually identify, and how many do we actually identify because we find the features first. I think that right now, our entire approach is based on the fact that you first find the features, and then you find the opinions corresponding to them. I don't even know how we would do if you took out the features, because you'd have nothing to anchor your opinion finding on. So there's another way to do this, and this is something that the people at IBM had done. They were looking for opinion phrases first, and then they were trying to anchor them to a particular feature in the sentence. But since we do it the other way, and we first find the features, I don't know, I think we'd find 0 opinion phrases. We'd have nothing to actually anchor it on. Yeah.
Does this assume, at the beginning of it, that you're dealing with hotels, and so you restrict your attributes and features to just hotels, as opposed to potential error if you were also trying to classify the domain of the item and do item clustering and so forth? So
that's absolutely right. So yeah, the first thing that the system does is takes the set of reviews, assumes that they're about hotels. Okay. Finds automatically the names of the features, and then finds the opinions. Now, if you have a set of reviews that's mixed, or might review more than one thing, I don't know. Yeah, I don't know what happened. It might find, yeah, it doesn't try to do that, so I can't even. It's not open domain, and it doesn't allow for mixed domain reviews. This is just for a single domain. So here's just one slide about what I was mentioning before at the beginning of the talk. For one particular featured name, such as room, you might find different opinion phrases, clean, dirty, and so on, that refer to one particular quality of the room, which is in this case cleanliness, and then you can find some others that refer to the room size. And the system simply clusters these opinion phrases based on actually based on co-occurrence, their co-occurrence in particular lexical patterns. So for example, you'll find on the web expressions such as clean or dirty, for example, or clean, even spotless. So you can cluster these opinion phrases and then try to figure out which particular quality they refer to. And you can do this using, there's some information in WordNet. Things like huge and small are linked in WordNet to the attribute they actually correspond to, which is size. So you can figure out that they actually refer to the size of something. If the information is not in WordNet, you can try to fabricate an attribute name. So we just said, what's the attribute that corresponds to clean? You can add a number of suffixes and try to figure out which one of them is a real word. So this is why, if you actually look at our demo, it's not cleanliness, it's actually cleanness, because that's something that the system fabricated and it's found on the web enough, so it thinks it's a real attribute. Finally, for each one of these clusters, you can determine how strong each opinion is relative to other opinions. So lexical patterns such as clean, even spotless, instantiate in this case. Clean, almost spotless, and clean but not spotless suggest that the strength of the first opinion is just higher than the strength of the second. And so basically you can use these constraints to determine an ordering of the opinions. So for example, for the room cleanness attribute, you will find that spotless is better than incredibly clean, and then very clean, and finally clean. So in conclusion, I've introduced a system named OPINE, which is a review mining system built on top of an information extraction system named KnowItAll, and it successfully extends its architecture for the task of mining reviews. And then I've shown that OPINE benefits a lot from using the web to compute statistics for product feature validation. And finally shown that OPINE benefits from taking into account context when trying to find the semantic orientation of a potential opinion word. So here are some of the things that we're currently working on. In the talk that I've given so far, we're actually identifying opinion phrases that correspond to a particular feature, but people have looked at how to identify positive or negative opinion sentences which correspond to a given feature. So if you're interested in, for instance, determining whether the sentence, the room was small but clean and overall great for the price, you're trying to determine whether that sentence overall is a positive or negative sentence that refers to room. So that's a much harder problem because you can have, in this sentence, for example, there are some things that are good about the room, some things that are bad about the room. However, it says overall great for the price. So it ends on a positive note. So the sentence, you can look at it as a positive sentence for this particular feature. Now, this is for just a particular feature, but you can also try to identify, and this is even harder, negative or positive sentences for the particular product. So if the sentence mentions a number of features for the product and has different semantic orientation opinions for each one of them, trying to figure out whether overall the sentence is positive or negative for the product, that's very hard, and some of you might know that. And finally, we're looking at not just finding opinions, but also finding specific problems. So, for example, in the consumer electronics domain, you have all these cases where people will say the laptop froze when he restarted it, or something like that. So in this case, you can find froze as a negative verb and figure out that something went wrong with the laptop, but you don't actually know what exactly went wrong. So something we're looking at is trying to see if you can identify specific problems. So these are 3 examples of cases in which a laptop freezes. We're trying to figure out if you can extract these and maybe cluster them in some way so you can have this additional output. And finally, we're trying to see how well some of the things that we've done for OPINE might apply to finding features of concepts which are mentioned in open domain text, such as, for instance, newspaper articles. And we think that identifying the features of concepts might work well. We don't know how well the opinion extraction is going to work, there are people who are working on opinion extractions from open domain text, and it's actually a very hard problem, much harder than that of extracting opinions from a consumer view. Thank you. No, we have not. Short answer.
Maybe this is a little like this. The old subdomain stuff, you know, it was always worried about what would it take to port to the next thing.
Right.
And so suppose we wanted to consider another community, another language group, another set of products, another, bulletin board type thing. Or how about, like instead of cross-language information retrieval, I want to do cross-language opinion assessment.
Right.
So I've got assessments in all the world's languages from everywhere. And now I gather this is a strength of your method, but I get worried when I start to see things like parsers.
Yeah, we got not that long question, which is, has more to it, with a very simple question of, can't you just get away with just using a part of speech tagger? Or even the part of speech tagger might be too much if you're trying to do this kind of cross-lingual stuff. I think we need at least a part of speech tagger. I think we need some processing of the sentence. We haven't tried to see if just using maybe a window to extract opinions would work well. So, yeah, I don't know.
So along these lines, years ago, a lot of people work on opinions just use 2 classes, and I think you're absolutely right to use 3 classes. Years ago, I had a bunch of comments that the AT&T operators received. Comments are euphemism; they're not nice. Okay, but they were labeled good, bad, and neutral. And you might ask, how could any of these comments be good? Well, the neutral ones could be fine. They're talking about something other than how much they hated the phone company. Right, but the good ones were when they were ranting about some other phone company rather than us. Now, what I did is I looked at words not just by one category at a time, but also 2 categories at a time, and it turned out there was quite a large number of words that were good and bad and never neutral. All right, and when you think about it, these are fairly predictable. These, like intensifiers, would be there. Okay. So very is not going to be a neutral word. All right, you don't know which direction it goes, but it's not neutral. There were some other words in there that I was a little more surprised by, like Mickey Mouse, outfit. Okay, how could these things be good? But it turned out they were good if they were predicated of the competition, and they were bad if they were predicated of us. Okay, and I think this question came up a couple of times already in they were asking, well, what if you're comparing this to that, all right? Then the same good or bad words just flip sense. It's a little like a negation, right?
That's right. I mean, that's a type of context that we, like I said, we haven't really taken into account unless we can detect that that's what happened. So, there are a lot of sentences where they will name the competition, the other company by name. So you can detect that they're talking about. But we're actually not. We're not using that information. We're just discarding it because it's not about the product at hand. But then, one thing that we did try. So we were looking at. You can compare these, different hotels based on what people said about each particular hotel by itself. But we also looked at just extracting comparison sentences and trying to see, can you extract from the web? Like if you're interested in knowing that, I don't know, you're interested in knowing how people feel about a particular Microsoft product versus how they feel about, maybe the products that the competitors make. We're looking at comparison sentences that you can maybe extract from the web for that particular product and specifically see what it was better or worse than. But what we did find, unfortunately, is that the number of sentences that we extracted varied widely with the particular product that we looked at. I mean, it just wasn't data that we can use.
Well, the specific suggestion would be to look for words that appear in 2 out of the 3 categories more than chance. Right. And I suspect they'd be interesting lists and a little surprising.
Yeah, we haven't looked at that, but go ahead.
As far as the work you're doing now going forward, would you characterize it more as trying to produce more outputs or more structure from the data versus trying to improve the sort of precision and recall of the work you've already done?
Yes.
And do you think there's headroom in improving that? The one thing that I think about in terms taking data from the web, then classifying it versus, and the loss of, degradation at each step as far as the loss of both when you classify it and then when you do entity extraction and then when you do clustering on items and so forth.
Right.
And that some of the more, sophisticated things that even get more data out of it seem worthwhile, but I guess the question is there still room to improve the previous steps so that you can...
Yes, I think there is plenty of room to improve some of the things that we've done. I mean, some of the things that we've done, especially for like product feature extraction, are very naive, right? I mean, you can imagine that you just achieve a much better precision even without going to the web by... Yeah, the reason we're doing that is because there are a lot of other people that are working, and some of them are sitting in this room, that have done, but some of them, are groups who are working on very sophisticated methods for example, extracting product features. And they've already written a number of papers this year. So, and their precision is quite high, even without going to the web, and just by mining the set of reviews at hand, they get pretty high precision. So, I don't know, I mean, we could definitely improve on what we have, but I don't know if you could improve on what they have, so.
So one thing is you've used
Yeah.
The polarity of the word in
Yeah.
the context of its feature and in the context of the sentence.
That's right.
Would you also, like when you go, do an experiment with just using a window,
Yeah.
maybe including the discourse connective within that window to allow it to flip without using structure?
Without using any structure, and just a
Can
window.
you take the overall polarity of the document into account? Because it seems to me that people usually feel, in the absence of anything else, people feel, one way or the other. They have strong opinions generally throughout.
Yeah.
So like, for example, the word hot, it will flip according to a feature, but it may simply have already been determined by the overall polarity of the
So one thing that we didn't look at, and this is something that, so I think it's related to your question, is we didn't look at what happens if you look not just at the sentence level, but maybe just taking into account the previous two sentences. So this is something that, again, other people have looked at, just to determine whether a particular opinion sentence is positive or negative. They say, well, if it occurs with strongly positive previous opinion sentences, then it's more likely to be positive.
Right.
And the same intuition, I think, can be applied to look at some of these words, which sometimes are neutral, like hot, but sometimes have polarity and determine their polarity. But we haven't looked at that, only because there was enough information so far at the sentence level. But you can imagine, for example, if you have the sentence, our room is really hot, you don't actually know by itself whether the word there is positive, negative, or neutral, but maybe looking at the previous sentence would tell you that. Yeah, that's something that we can definitely take into account, but we haven't done so far.
Well, I think if you're trying to do an experiment where you remove your reliance on the syntactic parser, or even part of speech, but just try to do it on a window size.
And then include the...
Then you'll have to include the larger context.
Yeah.
You might be able to compensate,
It's definitely the case
take
that...
out the parser, but include
larger context. It's definitely the case that people express, people cluster. The positive opinion sentences are clustered together, and then the negative ones are kind of clustered together. So I think just looking at maybe a window of 5 sentences would be enough to,
Because, one drawback of what you've proposed is that you do have these 10 to 11 syntactic heuristics and many expressions of patterns.
Yeah.
And maintaining such a rule-based system is quite difficult and will lead to difficulties when you move from domain to domain.
Yeah, I agree. Yeah.
So if you can replace that with various windows,
something that's very simple and can be ported,
it should be much easier.
I think that's a great suggestion. Yeah.
So sort of getting back to the question about other languages.
Yeah.
I know that it's not something that you've done so far, but have you thought about, would it be easier, do you think it would be easier to, if let's say you want to make this word for Italian, you just, get an Italian dependency parser and then sort of, rewrite some of the heuristics, or do you think it may actually work to, take parts of the English system, just translate the adjectives using some, available resource to...
Well, you can definitely translate some of the word lists, but you can... I think that you can translate some of the word lists. Now that I think about it, I don't know, maybe certain words behave differently. I'm not really sure.
there's going to be some noise. It's not going to be perfect, but just
I think you can translate some of the resources. One thing that I was reading this paper that was written in at one of the Tokyo research labs, and it was on extracting product features and evaluative expressions, and they've done all these things, and I couldn't understand why they were doing this, instead of just going to WordNet. Well, it turns out there's no WordNet for Japanese, and there are no, so some of the things that I've used and some of the assumptions that I've made about the syntactic structure of the sentence and so on cannot be made for other languages, in which case, you have to do something different that maybe relies a lot less on the syntax and a lot more on other types of information, like the contextual information.
Yeah, but then again, using the windows, that's something that seems like a reasonable.
Exactly.
Using a sliding window seems like a reasonable approximation for a number of languages. It's still going to be long distance issues, long distance dependency issues. But
that's right. Yeah. I was looking at the fact that they had much larger number of patterns to collect opinions and so on. And I couldn't understand why, and then it occurred to me that it was totally different language, totally different system. So yeah, they couldn't do some of those things.
So beyond using the kind of infrastructure of KnowItAll, which allows you to just generate tests and apply the patterns, did you use any of the data that is kind of the result of the KnowItAll processing? Did you use the KnowItAll databases itself?
No, the KnowItAll databases. KnowItAll is a system that so far was used for only a few concept classes. We're trying to populate a few concept classes and then finding instances of some binary relationships. But actually, those are mostly from the geography and administrative domains. So things like mayors, finding mayors of cities and things like that. So they have nothing to do with this. So I didn't use any of the pre-existing KnowItAll databases only because they have nothing to do with this domain. And they're really quite limited at this point. We just have there are a few classes and then a lot of instances, examples for each class, and a few relations and a lot of instances for the relations. But so far, there isn't a large, there's no domain for which we have a large model and then a large number of instances for the for the concept of the relationships. Yeah. No, there was no, we just sort of used the, when I say I use KnowItAll, what I mean is I use KnowItAll to go to the web and find the hits. That's actually mostly what I mean.
I have one more question. So how many, so in order to identify the product features, you also use syntactic patterns. Are those syntactic patterns or are those phrasal patterns?
In order to identify the potential features?
Yeah.
In order to identify the potential features, I parsed the reviews and just looked at noun phrases.
Okay, so it's also parsed.
Yes, it's parsed. What I found was, I actually ran just for that part. I did an experiment where I just used a part of speech tagger, and it worked better. Actually, the parser that I used, although it's good for certain things, has some problems. So I would have to actually patch it to find some noun phrases which it missed. Yeah, you don't actually need the parser for that, I don't think.
So how many patterns do you have originally? And I think you also have a number of patterns that were bootstrapped off of the web data. So
you mean just to validate features?
Right. So how many patterns do you have that that will extract?
Oh, I've used the ones that I think there are 3 or 4 original patterns.
Okay.
Which
X,
for
Y,
yeah.
X.
So that's for finding meronyms, and then if you want to find related concepts. So if you want to find, for instance, you have hotel, but you want to find neighborhood.
Right.
Related concepts occur in some of these same patterns, instantiate some of the same patterns with meronymy. But also I just use just co-occurrence information to find those, because a lot of them they're not actually there's a different relationship between the concept and the target concept, which in the case is hotel, and it's not meronymy. And I haven't looked at what specifically it is. I just look at the fact that it occurs.
Like 3 or 4 patterns.
Yes.
And then the rest are all co-occurrence based.
That's right. Yes. If you look at what the features are, there are all these recursive things like there's meronym of meronym and so on, and then there are these related concepts which I can't characterize any better than that. They're just there are other relations. There are things like, I guess the relationships between them and the target concept are things like located in and so on. But I haven't looked at those specific relationships. If it co-occurs with the word hotel in a small window on the web, I just assume it's related somehow